Hi there, my name is Charles Wasfan Sipa. Welcome to another presentation on differential equations. This time we're looking at worked examples involving growth and decay.
Okay, at this point let's look at something which is close to our health. In this case we're looking at a pain-relieving drug called morphine. And the problem reads as follows. The half-life of morphine in human blood is 3 hours. If initially there is 0.4 milligrams of morphine in the bloodstream, find the equation, in this case the function of time, for the amount of morphine in the blood at any time t. And then this following question asks, when does the amount of morphine drop below 0.1 milligram? And secondly, when does it drop to below 0.01 milligram? So I think from the situation we are faced with here, you can see that a drug of certain amount of 0.4 is introduced in the bloodstream. So what will happen, it will go down, which indicates that it's a kind of a behavior of which indicates exponential decay. So in solving this problem, already you must have some expectations on what kind of K we're going to get. Remember, the general solution for this kind of a problem was y of t equals to a0 e to the power kt. That is the solution we got from the general first order differential equation which describe exponential growth or decay. So now, by initial weight indicated here that initial of the drug is 0.4 milligrams, we translate that to mean that the initial value y of t of the function equals to a0 e to the power k 0, because time t is equal to 0, is equals to 0.4. So now, what we're going to do here, we'll note that solving this equation, we get to a point that a0 is equal to 0.4, because e to the power 0 is 1, then we get a0 equal to 0.4. So now we can now write this solution with the parameter a0 known to be equal to 0.4. So it will be 0.4 e to the power k t. It should be 0.4 e to the power k t. So what you can see is that we are one step away from getting the general expression for this kind of function that we'll get when we establish the value of k. But we're told here that the half-life of this substance is, of this drug is 3 hours. So what you could say here is that half, so that's 0.4 to be reduced to half, so half of 0.4, it will be added when time is 3 hours, so which means we calculate 0.4 here, e to the power 3k, substituting our time in hours by 3 hours. So then what you can deduce from this equation, dividing both sides by 0.4, we deduce that 3e to the power e to the exponent 3k is equals to half. And then now applying ln on both sides of this equation, we get that 3k is equals to ln of half. And this takes us to saying therefore k is equals to ln of half divided by 3. I hope my calculations are correct. As you can see, this k cannot be positive because ln of half is less than 0 divided by 3 is less than 0. So the actual number is supposed to be minus 0.23. Alright, so which means then now k is equal to minus 0.23. Now our function y of t is going to be 0.4 minus 0.23 t. So we've got that, and effectively their k is negative, so it's decay. So this is our expression which answers the question, the order, find the equation of the amount of morphine in the blood at any time t. So this is the expression which you can actually now use to predict what will be the amount of this drug in the bloodstream at a certain time in the future. But at this moment, we need to know at what time is the drug going to be 0.1, so that we can be able to answer that after that time it will be below, because at what time does it fall below 0.1 milligrams. So what we need to do now, we have to check the expression 0.4 e to the power minus 0.23 t equals to 0.1. So in this case here, this our known here is now the time t when this function will be at level 0.1. In other words, we can depict this by means of a picture. This way, it was 0.4 somewhere there, so it's decreasing exponentially this way. So we want to know at what time it's going to be equals to 0.1 somewhere there, say 1, 2, 3, and 4. So now we are looking for this time here. This is the time in question. So just taking the level there, 0.1 horizontally up to the graph, then go vertically down to get the position of the t we are looking for. So solving this analytically, what we do now, we divide both sides here by 0.4, which will give us that e to the exponent minus 0.23 t is equal to 0.1 over 0.4, which is equals to 0.25. Now, applying ln on both sides, I think we can all see that this will take us to, this is equivalent to saying minus 0.23 t is equals to ln of 0.25. Okay, so now what we're going to do now, we can now make t sub the formula by dividing both sides by minus 0.23. Note that this is a negative number, and this number here is the argument of linear is less than 1, is going to be negative. So we should be expecting here to get a positive t. So this is t equals to ln of 0.25 divided by 0.223, and that this is what gives us 6,027, which is approximately 6 hours. So now we've determined the time by which this level of morphine will be 0.1. So we expect that after 6 hours it will be below 0.1. So what we can do now, we can actually maybe even find the level of morphine when after 10 hours, in that case using the expression of the function. But otherwise, what we're asking, we've answered the question part A, and I'll leave the second part of the question for you to try to practice this kind of calculation and be careful with the numbers. I hope you are going to be able to bit by bit get experience in solving similar types of questions. Otherwise, at the moment, I think we need to look at a second example and see where it takes us to. Okay, at this point, let's look at another situation which involves Newton's law of cooling. It says here a certain liquid temperature is standing at 99 degrees Celsius. That's the temperature of the liquid when it's introduced to the room temperature environment. And we're also told that the ambient temperature, which you can write here, let's say YA, is equals to 25 degrees Celsius. And then the situation is, it is noted that after 2 minutes, the temperature is standing at 79 degrees Celsius. Let's say after 2 minutes, the temperature is 79 degrees Celsius. Now the question is, at what time t is this liquid going to be at 50 degrees Celsius? So to solve this kind of a problem, I hope you notice what the situation are given here. We're given a liquid at 99 degrees Celsius and the ambient temperature is 25 degrees Celsius, and it's observed that after 2 minutes the temperature is standing at 79. So to answer the question now, at what time t, at what time t is the temperature going to be 50 degrees? In other words, at what time t is y of t equals to 50? Now, to solve this kind of problem, we need to remember the model, the model of this type of solution, which is the first order differential equation y prime equals to k yt, which is temperature time t, minus the ambient temperature. And we also, in this case, we also should be remembering now that the solution to this equation was yt equals to a0, the general solution actually, the model solution was yt equals to a0 e to the power kt plus the ambient temperature. So now what we can do now, we can start. This is our temperature of the liquid, that is at time t equals to 0, which according to this model solution, it translates to saying y at 0 equals to a0 e to the power k0 plus our ambient temperature, in this case which is 25, is equals to 99. Now, solving this equation, we get to a point where we conclude that our A0 is going to be equals to 99 minus 20, 25, which is subtracting here, we get 74 degrees Celsius. So now we can write this expression as y of t, which is our general expression now, knowing A0, but still we need k. This is 74 e to the power kt plus 25. Now, I think it's time now to use the condition that after 2 minutes, the temperature is standing at 79. So what we do now, we say y at 2 equals to 79. So using this equation to evaluate the function at y of 2 is equal to 79, this is equivalent to saying 74 e to the power 2k plus 25 is equals to 79. Now simplifying here, we get 74. This is equivalent to 74 e to exponent 2k equals to 79 minus 25, which will be equals to 54. Now that will take us to dividing both sides by 74 e to the exponent 2k will be equals to 54 divided by 74. Now applying ln on both sides, we get that 2k is equal to ln of 54 over 74, and dividing both sides by 2, we get that k is equals to, or k is equals to 0, minus 0,26, and we expect it to be minus because this substance is cooling down, and clearly ln of this number, which is less than 1, must be negative, so divided by 2 is still negative. We get that. So now we have got y of t equal to 74 e to the power minus 0,26 t plus 25. So now this is the particular function which gives which is a solution to the Newton's law of cooling as a differential equation, and which you can now use to predict at what time the temperature will be 50 degrees Celsius. So what you need to do now is just need to set the right hand side here equals to 50, so 74 e to the exponent minus 0,26 t plus 25 equals to 50, and we see that this takes us to 74 e to the exponent minus 2t minus 0.26 t is equals to 25, and dividing both sides by 74, this is equivalent to say e to the exponent minus 0,26 t is equals to 25 divided by 74. again, what we need the to apply the logarithm function there on both sides, and we get that t is going to be equal to ln of 25 over 74 divided by 0 minus 0.26, which is roughly equals to, this is roughly equals to 2 decimal places 4.17. In this case, this will be 4.17. The tower time is in minutes, so say 4.17 minutes. So now we can choose now to maybe to try to predict or the value of the function maybe after 5 minutes, 10 minutes, and so on. That will be giving us the temperature, how far the temperature is decreased. Otherwise, I hope you've got an example here from which you can be able to set yourself on fire and try to do similar practice in a way that you become fluent in this kind of work.
Otherwise, at this point, I would like to say thank you for listening.